Hello friends, I'm Aadesh Tikhe. Today I'm excited to share my research paper idea on probability and polytopes. The title is Periodic Cotangent Function for forecasting the probability of teleporting a zero polytope proximity to the center or circumference in a two polytope. As we move towards explanation of the topic, I will give a light upon how I came across this topic. 6 months back at maths class, we were asked a question. If a point has to be made on a circle and only on that circle, which is 2D in nature, what is the probability of that point being near the center or being near the circumference? For now, pause the video for 2 minutes and try to solve this question on your own, or else you can watch the solution now. To solve this question, let's divide the radius of circle in two halves and make one more circle in the center of the circle. Now we can see both the circles have same center point. A smaller circle radius is half than the original circle's radius. If you look closely enough, we can see that if a point is made anywhere in the smaller circle, the point is near the center. But if it is made out of the smaller circle, the point is going to be near the circumference. Now let's calculate the area of both the circles, and to get a probability, let's divide the area of smaller circle by the area of bigger circle. Area of bigger circle is pi r square and the area of smaller circle would be pi r square by 4 because its radius is half the size of the bigger circle. Now we will divide the area of smaller circle by the bigger circle's area. We can cut the pi r square from the denominator and from the numerator, and we get 1 by 4 as a probability of the point being near the center, and if we want near the circumference, we can just subtract this probability by 1 and we get 3 by 4 as a probability for point being near the circumference. This motivated me to inquire about what if the same thing happens with a triangle or any n-sided polygon. Afterwards, I racked my brain and started to calculate the probability for different 2D polygons, which started from a triangle. Now, this time for triangle. For now, you can pause the video and try to solve on your own. And if you get the answer pi by 12 root 3, you can skip the triangle part of this video. Else, you can watch the solution. Now, for simplifying, let's take an equilateral triangle and let its side be x. Let's assume it has a center point named O. Now, let's create a line from the center point to the nearest side and name it L. The length of L is x by 2 root 3. If you wonder how I got the length of L, use the trigonometric identities to get the value of tan 30. Now, let's divide L into two parts and use the half of its line to draw a circle from its midpoint, like we did in the circle to get our probability. You might be wondering why I'm not using triangle or any other shape inside to differentiate that if the point is near the center or near the circumference. Because when I use another shape, it has different lengths from its center to its corner compared to that of its side. And therefore when the point is near to the corner of inner shape, it is actually more close to the circumference of the polygon of which we want to determine the probability than to the center point. Now let's solve the equation. So our radius is x by 4 root 3 and let's calculate the area of inner circle, and we will get pi x square by 48 as our area of the inner circle. Now let's divide this area by the equilateral triangle's area, which is x square root 3 by 4. So we got our final answer as pi by 12 root 3 for the probability of that point being near the center of the triangle. And for circumference, we can just simply subtract this pi by 12 root 3 from 1. Now let's calculate for the square. As we did for circle and triangle, you can apply the same logic and try to solve for square. If you get the answer as pi by 16, you can skip the square part of this video, or else you can watch the solution now. Let's make a line from the center of the circle to its nearest side. We can see that the line we made is half of the any side we choose. Now let's divide this line into two parts, and that would be x by 4. And this x by 4 is going to be our radius for the inner circle. Now let's calculate the area for our inner circle, which is pi x square by 16. Now let's divide this area of circle by area of square, and we would get our final answer as pi by 16. I performed these calculations for various polygons, including up to decagon manually, and derived the probability values. Then it caught my eyes that every polygon is going through the same method, and thereby I created a formula of pi cot in bracket 180 by x bracket close and whole thing divided by 4 by x. I used my mathematical knowledge and logic to derive this equation. These are the values which I calculate for other polygons. And then I compared them with this equation values by plotting them on a graph, and as we can see, the formula is giving us the same values that we calculated manually. In this equation, the x represents the number of sides for a particular polygon, and when we plot this on a graph, we can see that our answer for center probability never exceeds 1 by 4, no matter how big the value of x is. I have successfully completed a comprehensive study on this topic, which comes under the field of pure mathematics, and I'm eager to share my findings with the academic community. I have been aiming to publish it in reputable journals such as the Journal of American Mathematical Society or the Annals of Mathematics. However, I have encountered challenges in publishing process due to lack of mentorship or guidance. If you believe in the potential of this research, I would greatly appreciate any assistance or advice you could provide me in navigating the publishing process. If you have insights on how I can move forward, or if you can direct me toward the right channel for submission, I would be sincerely grateful. Your guidance would be immensely valuable to me. In the description of this video, I have added my contact details. Thank you for considering my request. I'm eager to take this next step in sharing my research with a wider mathematical community. Thank you.